In this tutorial, we're going to continue to talk about the derivative as a function. So we're going to start this off by looking at an example that says to find the points on the graph of f of t equals t cubed minus 12t plus 4 where the tangent line is horizontal. So let's take a look at this a little bit more closely to figure out exactly what it's asking for and what we know. So we're supposed to find the points. So my answer should have points in it, of course. Our graph is f of t equals t cubed minus 12t plus 4. And we know what tangent lines are, and it says where the tangent line is horizontal. Let's think about that in terms of slope, because we're talking about a tangent line that's hitting my graph once, and it's horizontal, so it's going to have a slope of 0. So that's important to know, because this is the only part of the function that we're curious about. So when we actually take a look at the graph of this, it actually looks something like this. So it's asking us for the points where the tangent line is horizontal. So when your tangent line is horizontal, that happens at maximums and minimums. In other words, if I take a look at my function, this right here would be a maximum point. It's the highest point in that general area. So this is my tangent line, and it does have a slope of 0, and it happens at some x value, okay? That's what I want to know. What is the actual point that that's happening at? The other place that this happens is down here at a minimum, and that will also occur. So this is also happening at some x value. We'll call it x2. That's what we're searching for, okay? So the first thing that we have to ask ourselves is, well, how do I use this slope concept when I'm given a function? And the first thing that we need to start thinking about is derivative. Now, if I were to find the derivative of my function f of t here, that would represent the slope. Now, if I want that slope to equal something in particular, then I just set my derivative equal to 0 and solve. So here's what it's going to look like. I'm first of all going to set up f of t, and I'm going to make sure that I can find f prime of t. So I'm just going to get this set up like so, and we're going to write everything in exactly as I see it. And I'm going to include a question mark in the end so that I know that that's not my final answer. So we're going to go through the process of finding the derivative using our power rule, and when we have several terms being added or subtracted, we can treat them as individual derivatives. For example, it would look like this. So I added my ddt's in front of each of my terms, and I separated them out using the signs that are given to me. So it's ddt of t cubed, that's my first term. I then have a minus sign that comes from the beginning, ddt of 12t, plus, because my 4 is being added, ddt of 4. So I'm going to find the individual derivatives of each of these. And this one is going to use my power rule. So I'm going to take my 3, bring it down in front, and reduce it by 1. So that becomes 3t squared. Minus the derivative of 12t, well, this is a linear function. Therefore, the derivative of it will just be the slope, my m, which is 12. And the last part is a constant. It is a number without a variable, therefore its derivative is 0. So this is actually my final function. This is my f prime of t. I want it to be equal to 0 though, because that's where I'm curious about. I'm wanting to know when this actually occurs. So I set this equal to 0, and I'm going to try to solve this. So I'm going to add 12 to both sides here, which gives me 12 equals 3t squared. I divide both sides by 3, and that will give me 4 equals t squared, and then I square root both sides, which is going to give me plus or minus 2. So that is how I find those x1 and x2's. So the x1 is at x equals negative 2, and x2 is positive 2. Now it actually wants us to find the full-blown points. The difference that you would be able to tell that in is if it said to find the x's or just to find the x values, something like that, but it wants us to find the points. So we actually have to take these values and plug them back in. So these are going to actually create coordinates. And to find those y values, I simply need to plug in these x's into my original function, which is this guy right here. So I plug in -2, and when I do that, I do get 20, and you can compute this on your own if you'd like. When I do +2, I get -12. So those two answers would be my final answer. So this particular function has horizontal tangents, in other words, maximums and minimums at these points. So let's take a look at another example. So in this one, we're going to calculate dg dt when t is equal to 1 for the function g of t equals t to the -cube plus 2 root t minus t to the -4/5. And this is a great example for showing out some different variations of our power rule. We need to know how to take the derivative of negative exponents, square roots, and negative rational exponents. And this is a great practice for it. So I'm going to start this off by saying dg dt is equal to, and I'm going to go ahead and separate all my terms. And of course, once you become comfortable doing this, you won't have to write out as many steps. But since this is our first time doing this, or maybe our second time, we're just going to make sure that we do this carefully. So this is going to be d dt of t to the -cube plus d dt, and I'm going to actually convert t to an exponent. We know that the square root is the same thing as an exponent of 1/2, so this is going to become something that you see a lot of. I'm not even joking, you're going to see that a lot. So minus d dt of t and then to the -4/5. So now that this is all set up, we're going to go through this entire thing. We're going to use our power rule and get all this settled up. So dg dt equals, so here we go. We are going to take our exponent here, bring it down as the coefficient, reduce it by 1. So -3 t to the -4 plus, and then here we have 1/2. I'm going to multiply that by the coefficient that's already there. 2 times 1/2 is 1, so I'm just left with a 1t, and then 1/2 minus 1 is -1/2. And then we have minus, and we're going to take this -4/5, multiply it by the coefficient here, which is going to become a negative number, and I already have subtraction here. So when we subtract a negative, that becomes a plus, and that's going to be 4/5 t, and now we have to reduce -4/5 by 1. If it's been a while since you've practiced fractions, we're going to practice it right now. So -4/5 minus 1 is the same thing as minusing 5/5. Okay, so we're going to have -4 minus 5, which is -9. So that's going to be my new rational exponent. So this is fine and great, but we still have to find out the derivative when t is equal to 1. That's what this part right here stands for. So we do this by going like this, dg dt when t is equal to 1 is equal to, and now we kind of solve it out. Not kind of, sorry, we do. So when we plug in 1, no matter what its exponent is, it will always become 1 no matter what. So t to the -4th, 1 to the -4th is 1. 1 times -3 is -3. T to the -1/2, 1 to the -1/2, it's 1. T to the -9/5, that's still going to become 1. 1 times 4/5 is 4/5. We add all these together, and we get -2 plus 4/5, which is the same exact thing as -10/5. So we're going to add that to 4/5. And negative 10 plus 4 is negative 6. Our denominator stays as 5. So that's how we would do a problem like that. And there's one more example that we must go over, and it's more or less about the way that the graphs are related, so the original versus its derivative. So let's go ahead and get that started. All right, so here we go. How is the graph of f of x equals x cubed minus 12x squared plus 36x minus 16 related to the derivative of f prime of x equals 3x squared minus 24x plus 36? Please understand that this function right here is the derivative function for this. Okay, so it's asking us what is the relationship between the original function and its derivative. I'm going to go ahead and graph both of them for you. So here we are, and please notice that my x-axis is in intervals of 2. So we have a cubic function for f of x, and it turns into quadratic, and that will always actually be a true statement, because remember that our power rule, we always reduce our leading exponent by 1. So cubics will always turn into quadratics. Quartics will always turn into cubics. Quadratics will always turn into linear, and so on and so forth. So what we want to do is kind of investigate different parts of our graph from the original to the derivative. And what's interesting is, the first thing that we're going to look at is what's interesting is where our horizontal tangents are. So if I take a look at my original function, I have horizontal tangents, in other words maximums and minimums, at 2 and at 6. When I take a look at where those horizontal tangents are in my derivative function, they happen to become x-intercepts. And a good question to ask is, well, is that always true? And the answer is yes. So every single time we have the slope of this function equaling 0, that's going to create the zeros of my derivative function. So that's going to be the very first thing that we want to note. So right here. So the f of x horizontal tangents are the x-intercepts on the f prime of x function. The next thing that we want to look at is, where is my original function positive and negative? And I'm going to be using positive with green and negative for red. So when I take a look at my original function, I have positive slopes from 0, it looks like, or close to 0, all the way up to 2. And that also happens from 6 and on forever. And please note that this looks somewhat Green Bay Packerish, which is beautiful. So please take a look at f prime of x on the right-hand side. And if you will notice, from 0 to 2 on this graph, I happen to be here. And from 6 and onwards, and I just paused this and noticed a mistake. So please bear with me. This 8 is not 8 here. It's supposed to be 6. Let's go ahead and fix that real quick. We're going to make this 2. We're going to put 4 here and then 8 out here. I am so sorry about that. Not the first time I've made a mistake on a video. 8 minus 4. That's a little inside joke. So, okay, so this x-intercept is actually at 6, and that makes more sense where the minimum is here. So hopefully that cleans it up a little bit. The reason why I noticed that is because when I take a look at my original function, I have positive slopes from 6 here all the way up to the right-hand side. And that needs to happen the same thing over here. So I start at 6 and then I go upwards from there. So where are the function, or where is this function in relation to where I have positive slopes? And the answer to that is that they're above the x-axis. Also something very important to note. So we're going to put that over here in our answer. So where f of x has positive slopes, that's where f prime of x is above the x-axis. And I'm sure that you can, from here, kind of create your own ending to this. So what's going to happen where my slopes are negative? And when we take a look at our graph, between 2 and 6, this is where all my negative slopes happen, right? So now I've got a Christmas graph, which is also amazing. So between 2 and 6, over here on my derivative function, where am I? And the answer to that is I'm below the x-axis. So negative slopes will put my function's derivative function below the x-axis. So we're going to go ahead and put that in our answer over here as well. So there we go. And once you have that written down, that's the end of this tutorial.